Segueing from our previous studies and the previous videos, we're looking at integration now and studying some rules and analyzing some rules where the result is based on an inverse trig function. So the integral is an inverse trig function of the nature that we've been studying. And from the previous work, we saw these results here for the derivative, and we're essentially going to reverse that, and I guess you could call this integration by recognition. And you've probably used that general strategy before, so recognizing the form and proceeding. Okay, so integration by recognition is our strategy. And we can see that here, okay, and we just basically reverse those forms. So if we have the integral of something in the form of 1 over the square root of a squared minus x squared dx, it comes out as, the integral comes out as inverse sine x on a plus c, and that's got a domain from negative a to a. Likewise for the second result there, so it's very similar once we understand preceding work. And lastly, the corresponding result for tan. Tan, as you've seen, tan has no restriction on the domain, it's any real number, all from our previous work. So the rest of the video now is going through 3 examples. There's 2 indefinite integrals, and when we find the indefinite integrals, that's often called the antiderivative. Okay, so the antiderivative, which is an indefinite integral, and then one definite integral to finish off the video. Okay, so the first example, we are integrating 1 over the square root of 9 minus 4x squared dx, and I've got the general form on the side there. So that's going to fit the inverse sine form of the integral. We note that we don't have a coefficient of 1 in front of the x squared, and so we factorize with that in mind first up. So we need to factorize that 4 out. So we proceed, and we've got the 4 factorized out on the denominator here as so. Now that'll have to be 9 on 4 minus x squared dx, and look, I've forgot my equal sign over there too, I couldn't help myself. Anyway, so you might be able to, if you have some algebra superpowers, you might be able to actually cut some of these steps out, but I just want to make sure everyone can follow it, so I'm going deliberately slow. Square root of 4 is 2, so that would leave a 2 outside of the square root of the rest. We can take a factor of half outside. It's one of the earliest rules of integration that we learned. Okay, so we clearly have an a value there, so we can let a, I'll write it over here, so let a equal, so a squared would be 9 on 4, so a would be 3 over 2. So we can follow the form now, equals half times inverse sine, followed like so, and we can finish off as 2x over 3. So 2x over 3 plus c. So half inverse sine 2x over 3 plus c. Okay, the second example, we've got the integral of 1 over 9 plus 4x squared dx, and we're going to use a similar strategy in that we write down the form that it seems to follow, the apparent form, the recognition part, and I've got that up there in light green. We've got to take the factor out 4, in other words. Again, if your algebra allows you to skip this step, you can do that. Like so, and then further inspection of the rule, however, says that we need to have a on the top here, and at the moment we have a 1 on the numerator. Need to think about that for a moment. We've got the coefficient of x squared sorted. It's now 1 inside the brackets there. We can move that 4 to the left outside of the integral summation symbol. We need to identify or let a equal something. Well, it is apparent that a squared is 9 on 4, so we let a equal 3 over 2. Sorry, that should be 3 over 2. I don't know why I wrote a. That's a 3. 3 over 2. We need to have 3 over 2 on the top. So what I would suggest you do is write what you want there on the top, and then you need to compensate for it. This is what we want. Okay, it's what we want. We've modified what we had. Now that quarter will go outside. That's okay. Originally it was a 1 on the numerator. We've multiplied the whole thing by 3 over 2, so we need to multiply it by the reciprocal. And we can do that outside along with the other fraction there to keep the overall value the same, and that stems back to our earlier work on integration. We've seen that before. That would be 2 over 12 or 1 over 6, and then we are able to just go ahead now with the rule, I think, because we have an a, we have an x identifiable, pretty easy. The result is 1/6 inverse 10 2x over 3 plus c. So in this final example here, it's a definite integral. We've got the form written there. We've got, you can verify with technology, even if you have a non-CAS calculator. So assuming you have something like a Texas Instruments Inspire non-CAS, you can still verify the answer, the final answer, by following those keystrokes. Other technologies operate in other ways, like Desmos or certain types of CAS calculators. So it is possible, and you should know how to use whatever machine you're allowed to use for in-class and exams to know how to verify an answer where required. It can also be handy just to see if you're correct too. So in the light green, the form, it can match the inverse sine integral, provided we have a 1 on the numerator, so that's easily dispensed with here. We can just put the 1 outside, as it's a constant, 9 minus 4x squared dx. Okay, so now you have the 1 on the numerator there. And we now need to factor out like we did last time on the denominator, so I'll go a bit quicker because we've seen this now. So we've got, after we take the square root, we've got 2 outside of the square root of 9 on 4 minus x squared dx, and now proceeding, we can take the 2 out as well. Square root 9 on 4 minus x squared dx. So again we see that a squared is 9 and 4, so let a equal 3 over 2, and that should fit the form pretty well now. I've made the calculation the same for the fractional part as the previous example, and so we can see that it's 3 on 2 times 3 on 2 times inverse sine 2x over 3 between 1 and 0, and we now compute that. First we expand it out if you need. So subbing in 1, subbing in 0, we have 3 over 2 times inverse sine of 2/3, which as an exact value, that's the answer. Okay, using that to verify it in exact form, we'll match the following calculation by just actually doing the calculations. It's approximately 1.095.